All right, let's talk a little bit about structural isomers. They're hydrocarbons, or really frankly, just about any organic molecule. You can depict branches or different substitutions and draw a very much different structure in some cases, but has the same formula. So it has to have a different formula, but a different structural arrangement of atoms. Those molecules do have different physical and chemical properties. So if we look at butane, you can have the normal straight chain butane, which is to the left, which is pretty much what we talked about in the previous video. So they call that N-butane because it's just a normal straight chain alkane. Now, we can take one of the CH3 groups off, which we'll call a methyl, and put it on this middle hydrogen. And so that's isobutane or 2-methyl propane. But it's more importantly for this particular video is that it is a different structure of a molecule that has the same formula as butane. And you notice the melting point and the boiling point, for example, are different. You can continue with, say, pentane. And as the molecule gets bigger, the number of structural isomers does increase. So this can become hairy quite quickly if you go past a few simple molecules, which is probably about where we're going to leave it, since this is a general chemistry course and not an organic chemistry course. We're just trying to introduce the concept. So if we got our normal straight chain pentane to the far left, then we pull the same type of deal that we did with the butane. We take one of the methyls from the end and stick it on the second carbon. We call that isopentane or 2-methyl butane. Notice it has different melting and boiling points. And then we pulled essentially the same deal. We take another CH3 off the end and put it on that same carbon that we attached the previous one to. And we get this sort of branch carbon where the central carbon does not have any hydrogens. It's bonded to 4 carbons. We call that neopentane or 2,2-dimethyl propane. And notice it even still has different melting point and boiling point than the other two. We'll look at a couple. We'll go to the paper. So let's look at a couple of examples. We'll start with a simple one and then work to a more complex one. So if we look at our basic propane structure, and I won't quite do all this for a bigger one, it'll be a little too difficult. Now, I've got 7 places for hydrogens, 1 place for chlorine. Just arbitrarily, I'll stick it there. The rest of the places are filled with hydrogen. Now I can draw more than one structural isomer, but I can't substitute for this one or this one because it's on the same carbon, and that would be essentially the same thing. Also, this carbon at the opposite side is considered to be the same because it'd be a flip of this molecule 180 degrees. So the only place I can put it that's different is on this middle carbon. Other structures would be considered the same as one you already drew. So I could put the chlorine on this one and fill out the rest. If we wanted to do that even with line structures, we could go, and that would be my basic propane, but then off of that, we would have a chlorine. And that would be the same thing. So then we'd have, and now the chlorine would be coming off of the middle one. And so you can see how they're different just with the line structures. Now, what if we went up to a larger hydrocarbon like hexane C6H14? So our basic structure would be 1, 2, 3, 4, 5, 6, right? or we would say CH3. Then you got CH2 4 times, and CH3. That is our normal or N hexane. Now we can pull the same type of trick a couple of different times. We can create a branch, and when we create a branch, you reduce the hydrogens by 1, but then you have another ending one, so the formula stays the same. Then we got CH2, CH2, and then a CH3. So that one works. And so our line structure would look like this: 1, 2, 3, 4, 5. And we would have a methyl group coming off, which is that CH3 group. We'll talk about naming a little bit later. Now, instead of putting it here, it would be different if I put it here. But if I put that methyl group here, it would be the same. And the ends aren't going to work because you would end up with this molecule again. So we can move it over 1 and say CH3, CH2, CH, and now the CH3 is coming off the middle carbon, CH2, CH3. So now we're going to have our same basic line structure, except the CH3 is off of that third carbon instead of the second one. That is 3 structures. Turns out hexane has 5 structures, so we're not quite done yet. Now we can move another methyl off into the middle. And so we have CH3, CH, CH3, CH, CH3, and then CH3. So a double substituted. And so now we'd have 1, 2, 3, 4, but we've got double substitutions on there. Last but certainly not least, we could substitute 2 onto the same carbon. So we have CH3, C, CH3, CH3, CH2, CH3. If you notice, they all have this formula C6H14, which is our normal hexane. Line structure, except now the CH3s both come off of the same carbon. And those would be the 5 structural isomers for our hexane C6H14. It is that's probably about as far as we'll go with it for this particular course, since it's an introductory level course. But that is the basics of how it works.